Thank you and welcome to my YouTube channel. So in this video, I would like to talk about the postulate of quantum mechanics and then use this postulate to motivate the Schrödinger's equation for a free particle. So let's begin. So to begin, I would like to talk about two main experiments in quantum physics. So the first one is the double slit experiment. So in the double slit experiment, we have a pair of double slits and we are shooting electrons or phonons from electron guns, for instance, towards the two double slits. So as the particle approaches the slit, they undergo diffraction. The same occurs at the other slits, and then they interfere constructively and destructively to produce an interference pattern. So I would like to show you an experimental result that was done for the double slit experiment using electrons. So as you can see, we have an interference pattern that has been produced by the electrons passing through the two slits. So the main point that I want to highlight from this experiment is the interference is resulting from the amplitude of the two electrons or two photons interfering constructively and destructively. That produces the interference pattern. So the interference pattern is produced by the amplitude. That's the point I wanted to highlight from this experiment. So the next experiment that I would like to talk about is the linear polarizer. So imagine we have an analyzer that only allows light polarized along the z-axis to pass through it. So let's say this is our z-axis, this is our y-axis, and then we have an incoming light polarized at an angle theta to the z-axis. So according to Malus' law, the measured intensity after the polarized light as passed through the analyzer goes as n cos squared theta, where we can say n is the number of photons and theta is the angle between the z-axis and the angle at which the light is polarized. So this result seems to make sense if we consider loads of different photons passing through the analyzer. However, if we consider an individual photon approaching or passing through the analyzer, the intensity goes as cos squared theta. And what this shows is for a single photon approaching the analyzer, there is a probability that is either going to be absorbed or is going to pass through the analyzer. And this led to the idea of decomposition, because we can imagine the state of our incoming photon as being composed of the z-axis and the y-axis with associated probabilities. So this is the point that I wanted to highlight for this experiment. So the idea of probability and also the idea of decomposition, that our incoming photon can be thought of as being made of a component polarized along the z-axis and a component polarized along the y-axis. So let's begin by putting all of this together and start making our postulates for quantum mechanics. So the first point that I would like to make is we can describe the state of our particle or a system of particles by something called the wave function, and the wave function tells us everything there is to know about the system. So we can describe our wave function as psi, which is a function of, say, the position and time. So going back to our linear polarizer, if we know the wave function of our incoming photon, we can deduce the probability that the incoming photon will either pass through the analyzer or gets absorbed by the analyzer. So knowing the wave function, we can get all the probabilities of obtaining certain measurements and also get to know everything there is to know about our photon. So everything about our photon or our system of particles is contained within this wave function. So that's the first postulate. The wave function is everything. Now, the second postulate that I'd like to talk about is related to decomposition. So we can write our wave function as a linear combination of some set of chosen states. So these chosen states are usually referred to as eigenfunctions, and we can represent them as, say, psi underscore a. Say maybe also as a function of position and time. So just like we can write a coordinate in terms of the x, y, and z axis, we can represent our wave function as a linear combination of these eigenfunctions. So for each of these chosen states, there is some measurement associated to it. So these measurements are usually referred to as the eigenvalue. So going back to our linear polarizer, we can represent our wave function of the phonon as a component polarized along the y-axis and a component polarized along the z-axis. So these two components in this case are our eigenfunctions, and then when they interact with the analyzer, one of these states gets chosen. So that leads to the next point that I want to make, that is when a measurement is made on a quantum system, the wave function collapses to one of the eigenfunctions. So we can represent our wave function as a linear combination of these eigenvalues. So let's write that down in an equation form. So this C underscore A is the amplitude of a certain eigenfunction, and psi underscore A is an eigenfunction. So as we stated before, when our wave function undergoes a measurement, one of these eigenfunctions gets chosen, and the probability that a certain eigenfunction gets chosen is given by this equation. So the probability that a certain eigenfunction gets chosen is given by the squared of the magnitude of its amplitude. Okay, so next I'd like to formulate a wave equation for quantum theory. So we know that each eigenfunction so we need a way to extract this eigenvalue. We need a way to get this measurement, right? So we can postulate that the equation for obtaining the eigenvalue for our given eigenfunction is h psi of A is equal to, so where E in this case is our eigenvalue and h is some operator that we are going to add on our eigenfunction in order to get our eigenvalue. So h could be any operator. It could be a derivative that we need to apply on the eigenfunction in order to get the eigenvalue. To summarize, we have our wave function. That is everything there is to know about a particle. It contains all the information. And this wave function is made up of a linear combination of some chosen states, which we call the eigenfunction, as written in this equation here. And each of these eigenfunctions have a measurement associated to them, which we call the eigenvalue. So this measurement could be energy, could be position, could be momentum. So we want to extract this measurement because that's the physical property that we're interested in. And in order to do that, we need to add on our eigenfunction with some sort of operator in order to get the physical measurement that we're interested in, which could be energy, which could be momentum, which could be position, right? And also, due to our interference pattern, we know that our equation needs to be linear. So the simplest equation that we can write for obtaining the eigenvalue is an equation of this form. So next, let's consider a free particle traveling through space with no potential energy associated to it. And we want to measure the energy of this free particle. Now, the first equation I'd like to write down is related to the de Broglie wavelength. So this equation relates the momentum to the wavelength of our particle. So we can write the momentum as being equals to h over lambda, where h is Planck's constant and lambda is the wavelength of our particle. Now, this can also be written as h bar multiplied by k. So h bar is h over 2 pi and k is 2 pi over lambda. Okay, so we also know that from the photoelectric effect, the energy of a particle, of a phonon, the energy of a phonon is given by h bar multiplied by w, where w is the angular frequency. Now, classically, for a free particle, the energy is only related to the kinetic energy because there's no potential associated with the particle. So we can write the energy of the particle as being equals to p squared over 2m, where p is the momentum. And then using our earlier relation from the de Broglie's wavelength, there we can write the energy as h bar squared k squared over 2m. So the reason why we are writing this equation here is we are drawing inspiration from the correspondence principle, which means that at some limit, whatever theory we develop should be similar to our classical results. And then using this inspiration, we are going to work with this equation. Okay, so from the photoelectric effect and the double slit experiment, it was obvious that particles and wave are the same thing. So therefore, we can start by writing the simplest wave equation we can for a particle. So going back to our wave equation, that we wrote earlier. So that is some operator adds on a eigenfunction to give us our eigenvalue or a measurement multiplied by our eigenfunction. So let's write a simplest equation that we can think of for our eigenfunction. So we can write this equation as something like this, where this is the time dependent part and this is the spatial part. So which we can rewrite as, okay, so in this situation, we are interested in the energy, right? So if we rewrite our operator acting on our wave function equals to E multiplied by our wave function, we are interested in the energy in this situation, right? So from the photoelectric effect, we know that the energy is equal to H bar omega. So the question now becomes, which operator can we find such that when it acts on our wave function here, we get our energy as a coefficient multiplied by our wave function. So that's the challenge. So let's consider H to be equal to IH bar. And now let's add this operator onto our wave function and see what we obtain. So we have IH bar multiplied by our wave function, which was E to the power minus I multiplied by. Now, if we find the derivative with respect to time, what we get is, so this simplifies as, so we already know that W is equal to E over H bar. So we can rewrite our equation as, so what this shows is we have our energy here, E, multiplied by our wave function here, psi of A. Using the operator that we used before, we can write this as IH bar is equal to E. So we can represent our energy as being equals to IH bar E delta T. Okay, so next, classically, we know that our energy is equal to P squared over 2M. Again, we are interested in our wave equation. So in this case, we have our energy as being equals to 2pm, the momentum squared over divided by 2 multiplied by the mass multiplied by the wave function. So we're interested in what operator can act on our wave function such that we get this coefficient as the energy coefficient, Pm, momentum squared over 2m. So again, let's consider our operator H as being equals to I squared H bar over 2m. Okay, so let's add this operator onto our wave function and let's see if we're able to get something similar to this. So we have I squared H bar squared over 2m. So when we do this derivative, what we get is I to the power 4 H bar over 2m. So this can be simplified as H bar squared K squared over 2m, or multiplied by that, where this is the wave function. Now remember from the de Broglie wavelength that our momentum is equal to H bar multiplied by K. So this shows that we have P squared over 2m multiplied by our wave, multiplied by our eigen function. So this proves that our P is then equals to H bar d over dr, which is normally written as this. So to summarize, we have our energy equals to H bar W. This was obtained from the photoelectric effect. And in this situation, we have the operator for this energy as being equals to HMI multiplied by H bar, the derivative with respect to time. And from our classical formula for the energy, which is equals to momentum squared over 2m, we get our energy as being equals to the operator given by I squared H bar squared. Okay, so drawing inspiration from our wave equation earlier, where we have some operator acting on our eigen function, giving us some eigenvalue E multiplied by our wave function, we can represent our operators now with this equation. So we can write our wave equation for a free particle as follows. So we can write it as, and this is the wave equation for a free particle. So now let's add potential. So let's consider a particle that is not moving freely but has some potential associated with it. So we can use our linearity, because our theory needs to be linear, again drawing inspiration from the interference pattern whereby the amplitude from the two waves adds together. This kind of shows that we need to consider our theory in a linear manner. So we can just simply add our potential to this equation and get our wave equation for a particle within a potential. So this can be written as minus h bar squared, the derivative with respect to position squared. This is our eigen function, plus, so we add our potential here. So v is our potential, which can be a function of position and time, multiplied by our wave function, and this is equal to IH. So this is our kinetic energy. So this operator was obtained using the formula for kinetic energy. So this is our kinetic energy, and this is the potential energy, and this is the total energy. And this is the time dependent Schrödinger's equation. So I would like to point out that this is not a mathematical derivation of the Schrödinger's equation. We are just postulating this equation, and then we are going to apply various potentials to this equation and see if the results we get from this make sense. So that's what we'll do in the next video. So we're trying to solve these equations for various potentials. So the direct potential, the simple harmonic potential, and then see whether the results we get from this make sense or describe what we see experimentally. So from that, I would like to end the video here, and always remember to stay in the present moment. Thank you.